I will discuss in this presentation some results we obtained at a country scale when we have done the assessment of the heat hazard risk in urban areas. As Eugen just mentioned, is one of the most important hazards in Romania at present. This is for two reasons. One is that it affects a lot the urban areas, and a lot of people and assets are in these areas. And the other thing which makes this topic so hot is that in the future the heat hazard is expected to increase not only in urban areas but also in the rest of the country. So I'm not sure the slides moves. Now you should see the context. Please confirm, because I'm not sure the presentation works. You see the context, I think, a slide with the context. So the research was done within a project funded by the European Space Agency. The project aimed to improve the capability of current satellite capabilities to retrieve land surface data at a global scale. This was the context of the project. We were just partners in this ESA project led by the Met Office in the UK, and we had to perform and provide the results for a user case study on urban heat island. This Suhi is surface urban heat island at country scale in Romania. So what you see was done within this context. First, this is something we already did, and it's still the context. We analyzed the surface urban heat island intensity at a country scale in all the cities above 30,000 inhabitants in Romania, actually. And you see here some results. It's a climatology of the surface urban heat island intensity in Romania, which allows the user to see the regional distribution of this topic, the surface urban heat island. I think a microphone is still open, so please, if you can turn it off, would be nice. So this is still the context. It's not the risk so far. It's just the intensity of the surface. You see here which are the extent of the worm in the cities larger than in the rural areas. It's just a context. But then we were interested in more applied things, such as to see which is the risk derived from the heat. This is heat hazard risk. And then, more than that, to provide an Earth observation-based service to produce some real-time or quasi-real-time heat hazard monitoring at country scale. So quite ambitious, I would say, but I think we already have some promising results. So the study area is the country. We have almost 80 cities in Romania with more than 30,000 inhabitants, and you see here the distribution of those cities based on the type of climate. The Köppen-Geiger climate types is also represented here, and also the size of the cities is just the study area. But what I would like to emphasize here, you see those black triangles. Those black triangles are the weather stations. So ground-based weather stations we have in our cities in Romania. Most of the cities, if not all, almost all, let's say, in most of the cities we have only one station. So with one station, it's quite difficult to extract the difference in temperature or in any other phenomena or any other meteorological element. The difference between urban and rural area is not possible based on only one station. That's why we do it since for many years now. We do such analysis using satellite data. which can provide aerial information that can cover both rural areas and the city areas. And we applied quite a traditional or well-known approach, a risk matrix approach, in which the risk is computed as a product between the heat hazard and vulnerability. I will go into details in the next slides. But for the time being, I will just say that the heat hazard was retrieved from land surface temperature, and the vulnerability was calculated from urban structure information. These local climate zones, that it's a concept and information very used now in urban climatology, and I will provide information later, and population density. So with this, we have the heat, which is the danger, the threat, and we also have the information about the city, the structure of the city, the land cover, and some information about the population, such as the density of population in different areas of the city. Of course, you could use, and we are planning to use different variables in the future, but for the time being, and for the sake of demonstration, and for what we are doing in this project, it was enough, I think. And we performed our research in 3 steps. We computed the heat hazard layer, the vulnerability layer, and then we combined these 2 layers into the heat hazard risk layer. So for computing the heat hazard, I mentioned that we used land surface temperature provided from satellite retrieved data. We used a modified MODIS LST data. It's the most common data set used in urban climatology. This MODIS data set provided by American satellites and sensors Terra and Aqua. It's a long-term data sets, long-term in terms of satellite data, which are not so long as in situ data, but we have more than 20 years now from these sensors, MODIS. And it's quite good for urban climatology and for climatology in general, because the spatial resolution is quite good. I mean, 1 kilometer. And the products come 4 times a day, two night times and two daytimes images. Of course, this is the ideal situation when you have clear sky situation. Otherwise, you could have less images. And the time span we focused on was 2018. This data set comes to the day, but of course, within the project, we had to have a limit, and this was the limit. To compute the heat hazard, because from the satellite, we just have the land surface temperature, but the hazard is different than the temperature, sometimes, if not always. But in this case, we computed the heat hazard as a cumulative number of situations, of cases, when this land surface temperature was above 40 during the daytime. So when you had the land surface temperature above 40 during the daytime is one case, and or the same parameter, land surface temperature, was above 20 this time during the nighttime. So these were the 2 thresholds for accumulating the land surface temperature, and we define this as the hazard, because in urban areas you need some threshold to see when the temperature is really a threat. It's not all the time a threat. When you have 10 degrees during the daytime or even the nighttime, it's not a threat. But when the temperature exceeds these thresholds, it can become the heat hazard. And I will provide details how we selected these thresholds, but maybe it's not the time here. I would like to finish the whole concept we did. And now you see some results in comparison to cities of Romania and to cities of the Romanian institutions are based in Bucharest, in Cluj-Napoca, the Romanian institutions from this project. And you see a very, very big difference in the heat hazard. And we know this in Romania for sure, but now you see in a quantitative manner. You see, for example, that in Bucharest we have in the center of Bucharest, you can have more than 140 situations when the threshold for the land surface temperature is above the values I mentioned before, whereas in Cluj you just have less than a half such situations, and in a very small area of Cluj, it's more fortunate from this point of view, Cluj, than Bucharest. So this is a hazard not valid or not so relevant for all the cities in Romania. But what we did in this project and in this presentation, I show you a country scale. So you could compare at country scale, which is the difference between the cities. So this was how we did the hazard, how we compute the hazard. And also the second step I mentioned is computing the vulnerability. And for vulnerability, the first variable introduced here is the local climate zones. This is a concept quite new, but so intense and so frequent now in urban climatology. Basically, this concept says that in a local climate zone 1, for example, you have tall buildings, you have compact buildings, most or sometimes only concrete, and these anthropic materials you can see here is compact high-rise. Then you decrease to local climate zone 2 and 3, for example, where you have smaller buildings and they are not so compact, they are a bit spread or spreader or so on. So you have compact mid-rise, compact low-rise, and then open high-rise. You can see that vegetation come here and so on. These 10 types of local climate zones are validated, and they are used and comparable in a standardized way to see a city. I mean, local climate zone 1 in Bucharest, it's local climate zone 1 in Cluj, it's local climate zone 1 in Oslo, it's the same. So it's a standard way to see the structure of the city, and behind this, there are measurements, of course, they are based on how the radiation is behaving in these areas and so on. So you see here the structure, but based on this, of course, you can have the land surface temperature in each of these zones, and we did it for all the cities in Romania. And this provides actually an information about the vulnerability. Which one is more vulnerable? Of course, local climate zone 1, where you have this compact structure of the city, is more vulnerable to heat than a more green area. And these were retrieved. It's an open data portal from the project VUDAP. At European scale, you can get any city in Europe, and these local climate zones were classified in 5 quintile. And then the quintile 1 is the lowest vulnerability, and quintile 5 is the higher vulnerability. We can discuss methodology later if needed. Another variable included to compute the vulnerability was the population density. Quite a simple parameter, simple to understand and simple to use, is the number of inhabitants, the population at 100 square meter. Again, an open data database from the Joint Research Center, and the same approach it was classified in 5 quantile-based classes. 5 is the highest vulnerability, 1 is the lowest vulnerability, and the average between the two local climate zone, which is the city structure, and the population density was here considered as the vulnerability layer. Of course, more data you have, more detailed data you have, better results you will get. This is something clear. Step 3, we computed the heat hazard, like a product between the heat hazard, the temperature, the land surface temperature, and the vulnerability. And 5 is heat hazard 5. Heat hazard risk 5 is the very high risk you see here, and heat hazard 1 is the lowest heat hazard risk in our cities. So I think it's quite a simple approach, but it's consistent with other approaches, and what is here is demonstrated now in some results. Here you have again an example from Bucharest. So starting, let's say, with this background, this topographic background, like Google Maps you see here in the left side, left-hand image, then you compute the heat hazard, which is the most red picture here. The heat hazard also classified in 5 classes. The vulnerability derived from the local climate zone, the vulnerability derived from the population density, and in the end, this is the result we were interested in, actually, the most right-hand picture, the heat hazard risk. What you see here, it's yellow, and from yellow, from light yellow to intense, to heavy red. Heavy red means, of course, heat hazard 5, which is the highest. And around Bucharest, you can notice, of course, in the rural areas or forest areas or so on, the heat hazard is not so important. The same for Cluj, a very different situation here. I mean, if you compare these two, you can see that the local climate zones and the vulnerability are quite red. I mean, in Cluj, you could have a high density of population, which is the fact. You still have some local climate zones that provide an input to this threat, which is the risk, but you don't have enough heat. You should make more fire there to be more close to Bucharest from this unwilling, actually, perspective. I'm just joking. And in the end, you get not so bad situation here, speaking about the heat hazard risk. Only the few parts in the central part of the city are not even red. They are just orange, which is a good situation in the end. When we have this for all the 77 cities in Romania. Based on what you saw for the time being, you can have statistics like this one. For example, just for 7 or 8 cities we have here, cities grouped by the climate zones, CFA, CFA, or CFB and DFB are the climate zones from Köppen, Geiger. And you see, for example, in Constanța, in Bucharest, very high risk during the nighttime or the daytime, the percentage, or in Cluj-Napoca or in Brașov, of course, very low percentage of the cities are affected by high heat hazard risk. Again, we have this for the whole country, and you will see maybe later. And now a geographical distribution of this heat hazard. It's only for the high and very high heat hazard risk. So 4-5 here in the legend, you see HHR 4-5. It means heat hazard 4 and 5 in the quantile based classification. And of course, this is something we expected. We have all the cities in the southern part of Romania more affected or more vulnerable to heat hazard risk than the cities inside the Carpathian chain, or even the cities outside the Carpathian chain, but in the western part of Romania, sometimes during the daytime, mainly they are affected by this hazard. And of course, you just have here an overview, a nice synthesis, I would say. You can connect visually here, but of course we have it quantitative. You can connect the heat hazard with the size of the city, and this is a nice example. I like it, Constanța, which is near the Black Sea coast, and you can see that during the nighttime, Constanța has a higher heat hazard than the same city during the daytime because of the proximity of the water. So of course, during the nighttime, the water remains a bit warmer than the city. You have the breeze circulation during the daytime, which makes the climate more bearable and the heat hazard lower during the daytime than expected in Constanța. Of course, not only the geographical position is important, but other factors too. And here is just an example. The heat hazard risk is in an inverse relation with the altitude. So higher the altitude of the city, lower the heat hazard risk. You see here some correlations. But the heat hazard risk, both by nighttime and by daytime, is very well related to the land surface temperature, and in some good correlation, I would say, with the size of the city, the area, and even more with the number of population, the inhabitants. And I mentioned the two objectives. The two objectives of the study. One was to perform a study and to get the situation from the heat hazard risk perspective in the Romanian cities. But if you remember, the second objective was to establish a service, a climate service. And here you have, I will show you a dynamic image after what I explain what you see here. So an overview of all the cities in Romania, and the heat hazard risk categories for each city. It's a global or not global, or the country scale, a country scale picture, very useful maybe, we hope so, for the national authorities and so on, to have at the same time, with the same methodology, the result of this risk. And I will stop, or I will share a different this one. Okay, so I hope you see now again this Google Earth background, and then the map of Romania with the cities. And I promise that I will show a dynamical view. You can, of course, focus on these cities, and immediately you will notice more details. You can compare cities which are close to each other, like Bucharest and Ploiești, for example. Let's take this example, different size of the cities, and of course, different heat hazard risk. Or you can focus to something like this, and you can get details for each district. And depending on the data you put in this tool, depending on the resolution of the data, you will get, of course, more details in the end. So I'll go back to this presentation, and it's just the end of it. So I will conclude that the satellite remote sensing is again an excellent potential demonstrated to support the analysis of thermal risk, of the heat hazard risk, in this case at urban level. We have now at our disposal available many times free of charge, or almost all the time free of charge, a lot of information for doing such study. And then the study reveals again the geographical context or some climatic factors, or of course the urban characteristics like structure, or density, and so on, are very important factors that influence the heat hazard risk at urban scale. So with this, I would end my presentation, and I'm here for your comments, questions, and recommendations, of course. Any feedback is welcome.
Thank you very much, Sorin. It was really interesting, the presentation, and indeed in Bucharest, it's unbearable sometimes the temperature. Fortunately, our institution is at the yellow edge of Bucharest, and yeah, if anybody has any questions for Sorin. Otherwise, I have a question regarding the products that you used. You mentioned for the LST you use MODIS products. And is there any particular reason you use that, and you didn't use some European products, satellite products?
Oh, this is, yeah. So one of the reasons is that they have the most consistent and the longest actually data sets available on the market. This 20 something, more than 20 years, long time series, no other data set from a satellite, European or States or from other sources, Japanese, they don't have such a long-term data set. And for climate, it's important to have long-term data sets. It's not enough for the traditional climate when you need 30 years, but still you got a very good image here. Then the spatial resolution, as I mentioned, and the temporal resolutions are quite useful, and they satisfy our needs. 1 kilometer, I repeat, for maybe there are people who are not so familiar with this. 1 kilometer and 4 images per day is quite good for climatology. And now, speaking about the shortcomings, of course, these analyses and the products and the outcomes are only for clear sky, because the satellite traditionally has this limitation to provide clear sky information. But since I think it's 2020 or 2019, we have from Landsat, EUMETSAT provides information for all sky. It's a product available now, freely available for all sky situations. They combined different products like emissivity, of course, but they used also vegetation and also land cover in general, not only vegetation, to do and to provide this product, which is all sky. The disadvantage there is that they have 3 to 5 kilometers. But this is one of our plans. We tested also Landsat, which is also a very nice product. They come with LST, the land surface temperature, at 100 meters, and you can get even better. But they have only very few, very sparse images. They don't have a continuity in the data. So you can do it for case studies or to combine with something else. It's not perfect. Nothing is perfect, actually. But our plan now, we got budget now for a national scale, national funds for a project to investigate what you do in WIMA-L in this project, to investigate the potential of integrating data to obtain a better product and, of course, a more accurate resolution for the outcomes and so on. So our plan is to use more in the next period also to stay with MODIS until they will finish their mission, because in some years they will finish this mission, MODIS, probably. This is what they say. But to combine these MODIS with different products and to obtain some more details. Of course, I'm sure that the pattern is already captured, and what you saw in this presentation will remain as a pattern. I mean, I will not expect that Cluj-Napoca will become hotter than the cities in the southern part in Romania using different data, but of course the resolution is important, and it is important for the local decision makers, because the purpose here was to see at a country scale everything at the same time and standard format, standard methodology, and so on. But for example, for the city hall in Cluj or in Iași or in Bucharest, they are not interested in other cities, actually. So they are interested in better resolution with finer resolution or more inputs. More fine input, like the age of the population. Instead of using only population density, you can use other factors like the age of the population or the income of the population, which makes them more vulnerable or less vulnerable to different risks. You can adapt or mitigate some risks using funds sometimes, or always. So such information would be useful at local scale, and this is our plan. So I hope I answered your question, and
And regarding your answer, I think from what I know, they started employing a lot of machine learning methods or they try to employ machine learning methods to fill up the missing data, the gaps.
Yeah. Yes, there are different techniques. We also used some techniques to fill the gaps in the special missing data because you don't have, using Clear Sky product, you don't have the whole coverage sometimes for the city, and we used these gap filling methods, but not machine learning. So this is a link that I would like to.
Yeah, from what I know, they started employing using machine learning and using different channels to fill up. And it's not your track here, but from what you know, do the authorities already employ results like this? I don't see it in Bucharest, for example.
In an indirect way, yes. I mean, also by the way, it's just the same context. It's also the same Norway grants context. They are now doing the climate adaptation plans for 8 cities in Romania. There are projects in the implementation phase. They will finish this year. And in these projects for climate adaptation, I think Cluj did it before, but some cities from Transylvania, a bit like Bistrița, like the county of Sibiu somewhere, Ploiești does it. It's an ongoing process to do this. In these climate adaptation plans, they asked for studies like this one. When we used, of course, ground-based information, but also such kind of information. We also did some studies for the World Bank also, urban scale in Romania using this. So in an indirect way, I say they use this. And my opinion is that the authorities are not so well prepared to get such products. So we are in the phase when we should adjust and we should work more with the local authorities and to tell them, look, you can get such a tool and use it for your long-term plans and even short-term plans, because this is not only for the next 30 years, but just for the next few years. It's what we have now.